Ever wonder how to make sense of data considering what you already know? Bayesian analysis might be your answer. Welcome to Ford Academy. In this video, we will be considering an introduction to Bayesian analysis. We will discuss what is Bayesian analysis, why use Bayesian analysis, advantages and disadvantages of Bayesian analysis, and how to carry out Bayesian analysis. So stay tuned. Bayesian analysis is a statistical analysis that answers research questions about unknown parameters of statistical models by using probability statements. It treats parameters as uncertain quantities described by probability distributions. The key strength of Bayesian analysis is prior knowledge, which can be incorporated using a power distribution. Prior knowledge could be based on past experiments, general beliefs, or even opinions from experts, statistical consultants, and so on. After incorporating the power distribution, new data is now brought in using the likelihood function. The likelihood function reflects how probable the data is for different parameter values. By applying Bayes' theorem, the prior and likelihood are combined to form a posterior distribution. This represents the updated belief about the parameters after considering both prior knowledge and new data. In essence, Bayesian analysis allows you to learn and update your understanding as you collect more information. Bayesian analysis allows you to integrate existing knowledge or beliefs into the analysis through power distributions. This can be useful when data is scarce. So let's consider these two examples. First, if you have an educated guess about the likelihood of a coin landing on Earth based on its material, you can factor that into your analysis of coin toss result. Also, if you are analyzing a new drug's effectiveness with a small sample, you can incorporate existing knowledge about similar drugs to strengthen your conclusions. The outputs of Bayesian analysis like posterior probabilities and credible intervals are naturally interpretable in terms of probabilities. This makes it easier to understand the likelihood of a hypothesis being true or the range within which an unknown parameter is likely to fall. This can be advantageous when you are dealing with real-world scenarios that often involve multiple interacting factors. Bayesian methods are proficient at handling intricate models with numerous parameters. Bayesian methods are well suited for handling complexity, allowing you to create more significant models that better reflect real-world situations. As you acquire more data, Bayesian analysis seamlessly updates its conclusion by incorporating the new information. This ongoing learning process reflects how our understanding of the world evolves with fresh evidence. This is particularly useful in fields where knowledge is constantly accumulating, such as medicine, machine learning, and so on. Some situations where Bayesian analysis is much more preferred include when we have a small data set. When you have small data sets, incorporating power knowledge through Bayesian methods can strengthen your analysis and provide more meaningful results. When you have data from multiple sources or experiments, Bayesian analysis can effectively combine this information to arrive at a more comprehensive understanding. In fields like medicine, Bayesian analysis can be used to make predictions tailored to individual circumstances by considering a person's specific background and data. While Bayesian analysis offers many advantages, there are also some drawbacks to consider. Choosing the appropriate power distributions can be challenging. There is no single correct way to do it, and the analyst's judgment plays a role. A poorly chosen power can significantly influence the results, potentially biasing them in a certain direction. Performing complex Bayesian analysis can be computationally expensive, especially for models with many parameters. This can necessitate specialized software and powerful computing resources. Understanding and interpreting Bayesian analysis can require more statistical expertise compared to frequentist methods. This can make it difficult for others to assess the validity of the result and potentially hinder reproducibility. There's no established method for selecting the best power distributions. While some techniques exist to help assess the sensitivity of results to power choices, it can still be a subjective process. If you lack a strong foundation in Bayesian statistics, the complexity of the analysis and results might be challenging to grasp. If your power distributions are very strong or certain, they might overshadow the data and lead to biased conclusions. Firstly, You have to be clear about what you are trying to learn and the type of data you have available. This will guide your model selection and power distributions. Select a probability distribution that reflects the relationship between your variables. Common choices include linear regression, Poisson models, logistic regression, and so on. This is where you incorporate your existing knowledge or beliefs into the parameters in your model. You can choose informative pairs if you have strong beliefs, or non-informative pairs if your knowledge is limited. There are also resources to help you select appropriate pairs. This is the heart of the Bayesian analysis. It combines your power distributions with the likelihood function using Bayes' theorem. It determines how well your model fits the data. There are two main approaches for obtaining the power distribution, which are the analytical solutions and computational methods. With regards to the analytical solution, you might be able to derive the posterior distribution mathematically for certain simple models, while in most cases, you have to rely on specialized software like Stan or JAX to perform the Markov chain Monte Carlo simulations to approximate the posterior distribution. Once you have the posterior distribution, you can extract several information like the posterior mean, which represents the most likely value for the parameter based on your data and pairs. The credible intervals, which captures the range of values within which the parameter is likely to fall with a certain probability. And the predictive distributions, you can use the posterior to make predictions about new data points. And lastly, you have to validate and interpret. Assess the convergence of your MCMC simulations and ensure your model fits the data reasonably well. Finally, interpret your results in the context of your research question. It is very important to interpret your results in the context of your research question. Thank you for watching.